Thanks for joining us this morning on this webinar on using an OCS in a 12-volt environment. We'll just jump straight into the presentation, and if you have any questions, we can get to those at the end.
Welcome to today's tutorial. Let's get started. Let's have a look at our agenda for today. Today we're looking at using OCS in a 12-volt environment. First, we'll look at some common 12-volt applications, and then we'll look at which Horner products are compatible with 12-volt DC. We'll talk about some general considerations of 12-volt applications, as well as some unique issues that can occur and some solutions for those issues. We'll talk about popular features for 12-volt applications, and then we'll have demonstrations throughout, and as always we'll finish with a Q&A session. What are some common 12-volt DC applications? First, any application that's battery powered from a 12-volt standpoint is of course a 12-volt application. Mobile applications, marine applications, and solar applications are all common applications with a 12-volt environment. What you'll find in all of these cases is that some applications are 12 volts and some applications in the same areas are 24 volts. So always check to see what the voltage is in your case before you proceed. Next, which OCS products are compatible with 12 volts DC? By compatible we mean two things. The first thing we mean is they have a wide voltage range, typically 10 to 30 volts DC on the power supply side. And secondly, for any digital inputs that are part of the OCS, are those inputs compatible with 12 volt DC signals? Here all the models you see on the screen, as well as the RCC, are the models that meet these requirements. So those are the X5 and X10 from the Micro OCS family, the XLE and XLT, as well as the XL series and the new XL Prime series. If you need to add some additional expansion I/O that's 12 volt compatible, here your choices are the Smart Block and Smart Mod. So these products all have the appropriate on-off thresholds to be supportive of 12 volt inputs. Let's talk about some other considerations before we go any further. The first thing to consider is the fact that when you're talking about battery voltages, it can be useful to monitor the supply voltage using an OCS analog input. That way you can do things like set alarm conditions or data logging. So how will we monitor supply voltage, which could be anywhere between 9 volts and 16 volts typically, when we have a 0 to 10 volt limit on our analog inputs on the OCS? Here we'll use a simple voltage divider. What we usually do is use a voltage divider where both of the resistors are equal, and then run the center point between the resistors into the analog input. Then we're effectively measuring half the voltage. Then we can use some simple math to be able to determine what the supply voltage is. If there is 12 volts of supply voltage, we'll see 6 volts on the analog input. Now let's demonstrate that in Cscape. I have the circuit that you see there on the screen, and I have a variable DC supply that I can vary up to 20 volts, and I have a voltage divider using 10k ohm quarter watt resistors, and from the center point of those resistors I've run that into an analog input on an XL4, and I'm monitoring the supply voltage. We'll start from the hardware configuration. Before I configure the hardware in Cscape, because I'm using an XL4 Model 2, there are jumpers that I have to move to support 0 to 10 volts on the input range. The default is 4 to 20 milliamps. So the first thing I did was pull off the back cover, move the jumper for channel 1, and then put the cover back on. Next, in hardware configuration, I went to the local I/O tab and hit config module setup. Then on the analog input side, here I set the voltage or input range to 0 to 10 volts. I also applied some filtering to steady the readings out a bit. That's all the config needed. Next I set up some alarm conditions so that when I hit 17 volts, that's a high alarm condition, and when the voltage hits 11 volts, a low alarm will trigger because that's lower than I want, as the OCS will power off at just under 10 volts. If I go to the graphics editor and pull up config alarm, you'll see I've assigned up to 16 alarms to a variable based array. Then for demonstration purposes, I've set an under voltage alarm at 11 volts from a descriptive standpoint, and an over voltage alarm at 17 volts, but I need to add some logic to be able to implement those alarms. So let's look at the logic. Here's my under voltage alarm, which is the first member of the alarm array. So if I hit 11 volts, that's an undervoltage alarm. Then if I get back above 11.2, we'll call that a return to normal. On the high voltage side, if I hit 17 volts, that's a high alarm, and if I get back below 16.8 volts, it returns to normal. Next, how did I take the actual analog counts and convert them over to volts? For that, I only needed two function blocks. First of all, you likely know that analog inputs come in as integers scaled from 0 to 32,000. So we need to convert that over to a floating point value or a real value. I used the conversion function to take a variable that was mapped to analog input 1 and map it over to a real type variable. Then I used a scaling function. The scaling that I started with was 0 to 32,000 on the analog side, and that goes to 0 to 20 volts on the voltage side. These numbers look different from what I just talked about because I took a digital voltmeter and I optimized the scaling for between 5 volts and 16 volts. So it scales outside those limits, but it optimizes the accuracy between those 2 points. Now let's look at the OCS. So this is my variable supply, which ranges up to 20 volts and down to just a few volts. Here's my XL4, which effectively has the analog circuitry connected to a 10k voltage divider with two 10k resistors running into analog input number 1, which is off screen. As I vary the supply voltage, you should be able to see that the OCS is monitoring it the whole way up. And then, once I get to 17 volts, that will trigger an alarm condition. Now, I'll acknowledge that alarm condition. As my voltage drops below 16.8, you'll see I've returned to normal. Similarly, on the low end, once I go below 11 volts, you'll see another alarm. Once again, I'll acknowledge that alarm condition. Then, once I get back over 11.2, we've again returned to normal. For all of the OCS somewhere below 10 volts, you'll see it won't have enough voltage to be able to operate. So I'll find that point here. So as I go below 11 volts, that will trigger my alarm condition. And as I continue to go lower, as low as 9.5 volts, eventually the OCS will power down. Then when I go back above 10, you'll see I'll go up as far as 13 here and it reboots. So when you're depending on low levels like that and you're depending on a battery, it's valuable to monitor that. Next, let's talk about 3 unique 12 volt DC issues that you run into in mobile applications. They're all related to the fact that you very often have a battery and an alternator in these systems. The 3 issues are battery drain, which is a low voltage condition, engine cranking, which is another low voltage condition, and then load dump, which is a high voltage condition. Let's take a look at these one at a time. Let's start with the battery drain issue. So let's say the OCS has been left on and the battery is not charging. So here the battery is slowly draining and the voltage is slowly dropping until it gets to the OCS threshold between 9 and 10 volts. And at that point the OCS will power down. When the OCS powered down, it's possible that the reduction in load from the OCS being off is enough for the battery voltage to go back up enough for the OCS to try and turn back on again. Then of course the voltage drops again and the cycle repeats. One of the ways to alleviate this issue is by using a DC to DC converter. That is a power supply that can be used to convert one DC voltage to another. Here we'll use a DC to DC converter that's going to convert 12 volts up to 24 volts. One of the reasons why this can actually help is because a lot of DC to DC converters have some hysteresis built into them, so they shut down at a lower voltage than they turn on. So let's talk about the advantages of adding a DC to DC converter to your system. First of all, as mentioned, it alleviates the battery drain cycling issue. The other thing is a high quality DC to DC converter will also provide galvanic isolation. So it'll protect against inrush, overvoltage, and it will also provide a 24 volt DC output, which would allow any OCS product to be used from the standpoint of supply voltage. There are disadvantages. DC to DC converters can be expensive, and they can also be physically large, especially the high quality ones. The next issue we'll talk about is engine cranking. When an engine is started, the voltage can drop significantly, often well below the OCS lower voltage limit, and it can stay there for a few hundred milliseconds, and then it can take a few seconds in some cases to get all the way back up to the normal voltage range after the start. This issue is exacerbated by cold weather. So how can we deal with this? Well, first of all, in a lot of applications, this is not a problem, but if it is a problem that you want to solve, you can use a boosting voltage regulator. We want to take lower voltages that we might be getting from the supply voltage and boost those up to the point where the OCS will reset during at least a significant number of these engine cranking type scenarios. We want to take lower voltages that we might be getting from the supply voltage and boost those up to the point where the OCS will reset during at least a significant number of these engine cranking type scenarios. This circuit can allow the OCS to maintain operation down to 5 volts. The advantages of using a boosting voltage regulator is that it will greatly reduce the impact of engine cranking, and they are relatively inexpensive. The disadvantages are that they are not readily available from mainstream manufacturers. Now we'll demonstrate using a boost regulator in between the supply voltage and the OCS to boost the voltage to the point where we at least a lot of the time won't have any engine cranking resets. So we'll go straight to the OCS. Right now I have the OCS connected to the supply voltage directly. I'm going to bring in line this boosting regulator between the power supply and the OCS. So I'll power down the OCS because this is the full voltage here from the supply, and I'm going to replace it with the output from the regulator. So let's plug this in. The OCS will need to boot up, which will take a moment. Now we're still monitoring the supply voltage that hasn't changed, but the voltage that's keeping the OCS running is now coming from this boost regulator. So let's see what happens when I drop the voltage down to the level at which it reset before, which was around 9.5 volts. Again, once I go below 11 volts, my alarm condition is triggered, and I'll continue to lower the voltage. Now we're definitely below that level, and you'll notice that we're still running. That's because this boost regulator is providing ample voltage and power for the OCS to run. So let's take a look at what that voltage is. I'll pull in a multimeter, select DC voltage, and then I'll go ahead and put it where we can see it. Now I'll monitor the output voltage from this boost regulator, and you'll see in a moment that it's putting out around 15 volts. The way this regulator works is there is a potentiometer, or at least some level of adjustment for the output voltage. Even though the supply voltage is currently about 9.16 volts, there's little difference in the readout between the OCS and the supply itself. It's around 9.2 volts, and the output from the boost regulator is actually 14 volts. So let's monitor that as we turn the voltage down further, and you'll notice as the voltage continues to go down, the voltage going to the OCS from the boost regulator is holding steady at about 15 volts. So I'll move this out of the way now. And let's see at what point does the OCS finally reset with this boost regulator in line. It should be somewhere around the 5 volt range, and if we go down slowly it will probably go below 5 volts quite a bit. Now keep in mind when you're doing a crank of this engine, the voltage is going to drop quickly. It's not going to drop slowly, so you're not going to get this kind of performance under normal conditions. You can see we'll get down just below 4 volts when the OCS finally powers down, and then I'll put it back up to about 8 volts and you'll see the OCS boots up again. So you can get down to about 5 volts comfortably using a boost regulator like the one I've shown here. The next issue we'll look at is called a load dump. A load dump is a high transient voltage issue. So when a large load is switched off from in a 12 volt DC system, it's possible that the voltage will jump briefly until it comes back again into regulation. The worst case scenario when this happens is when the battery is disconnected from the alternator under load, causing a very large voltage spike. So how do we deal with this? Well, first of all, the good news is that for the non-worst case scenarios, there already is a lot of transient protection built into the OCS power supply circuitry. So in a lot of cases, if it's not that worst case scenario, then you won't get these type of transients that you need to worry about. However, if you want to add additional protection, you can add an automotive grade TVS diode across the power supply input to the OCS, and that will provide that load dump protection. That provides additional protection over and above the transient protection built into the OCS, and they're very inexpensive components. The disadvantage is that this is an electronic component in a leaded package, which takes a bit of care to be installed in a typical control enclosure type application. Now let's talk about some additional features that are popular with automotive or mobile type applications. One of the more popular features is J1939 communications. J1939 is a CAN-based communications and diagnostics protocol among vehicle components, and at this point it's used in just about any mobile application or application involving an engine. The OCS, including any of the units that have two CAN ports, can support J1939 as standard. For OCSs with a single CAN port, it's an option that you can acquire to add the J1939 capability to your unit via the CAN port. By having J1939 supported, you have the ability to monitor key data that is being generated by the engine control module without adding any parallel instrumentation. Finally, we'll talk about video cameras. They can be useful for providing operators with a unique view of the machine that may be showing something that otherwise the operator couldn't easily see on a piece of mobile equipment. The OCS supports the USB video standard, which is the standard supported by webcams. There's plenty of ruggedized USB cameras available from a variety of industrial suppliers. You could have up to 4 cameras connected to a USB hub that's then connected to the OCS through a single USB-A port. The channel number for each camera will automatically be assigned based on power-up order. That concludes our demonstration for today. Thank you for joining me for today's tutorial, and the Q&A session will begin shortly.
Okay, so next week we have using XL and XLEE as remote I/O, and the registration link is up in the webinar section of the website if you would like to come and see that. Thanks for joining us today on this webinar. Hope it was of benefit to you, and we shall see you next week.